Welcome to Feza Gürsey Center for Physics and Mathematics Higher Structures seminar series. Today our speaker is David Ayala, and we are very happy to have him in our seminar series. And he will going to tell us about factorization homology of higher categories. So please, David.
Okay. Well, thanks for this invitation. Um, I I'm enthusiastic about connecting with each of you on this call. Um, because I don't have personal relations with you, I sort of made a guess about background that I really welcome you to please stop me with questions anytime, and I'm happy to redirect where this talk goes accordingly. So please interrupt at any time. Um, so all of this work that I'm going to talk about is joint with John Francis, my collaborator, and a considerable portion is also joint with Aaron Maselji and Nick Rosenblum. So what I figured I'd do is I'd start by giving a heuristic description of the main result, talk about some applications of it, and then I'll come back and state the main result more precisely and start to outline what the key technical elements of its proof are. So uh, here's the main theorem again, stated heuristically. So each rigid braided monoidal category uh, over a commutative ring, and let's call that thing R, determines a three-dimensional TQFT. And I think of that as an assignment of to a three-dimensional manifold, a chain complex. And it's intended to this chain complex in the context of QFT is intended to abstract the point operators and the line operators of the theory, not the surface or deeper operators, but just the point and line operators. So again, to each rigid braided monoidal category, uh, there's a TQFT that is rigorously constructed, and it constructs the point and line observables of this you know of this theory. Now, there's a lot of decoration on this slide outside of what I said, so I'll just point out that uh, so braided monoidal, um, it can be abstract to what I'll call n minus one monoidal or en minus one monoidal. And what's meant by that is n minus one commuting monoidal directions that are all compatible. So braided monoidal, braided here means is where n minus one is equal to two. And so so for braided monoidal categories, this is constructing a three-dimensional TQFT. Uh, I'll also comment that this chain complex, as I will mention, H0 of it, the zeroth homology, will just be a K module. Uh, and this will be in example, we'll see an example soon, but I'll mention it here so you have it in mind. This will be the skein module of the three manifold. So what this main theorem is doing in particular is constructing a chain complex valued three-dimensional TQFT whose zeroth homology recovers skein modules. Um, I'll get to that pretty soon. Okay, so it's not any old assignment of a manifold to a chain complex. but it's such that it has these particular features. So uh, the values on Euclidean spaces. So I said that this is a three-dimensional TQFT. It can be evaluated on any manifold of dimension less than or equal to 3. When evaluated on R2, it's the chain complex of chains on the moduli space of objects of R. And when evaluated on R3, it's the endomorphisms of the unit of this monoidal category R. So we'll see how to use both of these features um, to recover the Jones polynomial in just a couple minutes. It has these other features. For one, it's, I would say, I would give this the slogan continuous. So there's an action of the continuous group, of the topological group of framed diffeomorphisms of M on this chain complex. And just appreciate that uh, this is better than just saying that this chain complex is diff invariant. And it's, of course, also better than just saying the mapping class group acts on the zeroth homology. It's a full-on action of the continuous group of diffeomorphisms. Um, so actually, I'll just mention right here, one feature of this then is that one can construct, for instance, one can take the rth homology of diff and pair it with the minus rth homology of, for instance, endomorphisms of the unit, and just reflect on how uh, it's exactly like HOMs in chain complexes that tend to have negative homology. So looking at the negative rth homology um, is not necessarily zero. So this supplies a way of producing, um, even if one's only interested in the zeroth homology of this, this action supplies a way of producing elements in here from positive degree elements in the diffeomorphisms. So I'm just giving, uh, just emphasizing the role that uh, this feature plays of this construction. Continuing, this construction, this assignment of a chain complex to a manifold, is functorial in two senses. One is with respect to open embeddings. So given an open embedding, Mn to n, that determines a map of chain complexes. But also, given a proper fiber bundle from M to B. So an example to keep in mind, even though it seems silly, is where B is R2 and M is R2 cross S1, then simply the projection is a proper fiber bundle. Um, and that determines a map then this way, the opposite way. So this main theorem that I'm discussing, um, it just automatically supplies this kind of functoriality. So this continuity, this functoriality. And now we're one to want to compute some values. Just knowing these values, well, you know that every three manifold can be broken up into smaller parts, similar with every two manifold. Um, and some three manifolds, such as this one, arise as a surface cross a one manifold. So you'd like to know if there's like a Fubini theorem for product manifolds, and also an excision theorem for local to global results. So that would aid in computations of these values. And indeed, this construction satisfies a Fubini result. So given a surface and a curve, then this chain complex can be computed as if you already happen to know the what's called alpha factorization homology, uh, followed by the beta factorization homology. Anyway, there's a formula that aids in computations when the three manifold splits as a product. And if one, so here's, I'm talking about this three-dimensional theory, but here's a two-dimensional schematic of a way of gluing two manifolds together along a common boundary. So if you have a three manifold that's the result of gluing two three manifolds with boundary along a common boundary, then there's this excision statement that this value can be computed in terms of these values along um, essentially the value on the boundary. So just like the axioms of a generalized homology theory, just knowing excision and like homotopy invariance and functoriality, just from that, one can compute the value of homology on lots and lots of things without needing to know the exact definition of homology. That's how I'm trying to advocate to think of this construction of this main theorem presently. So I haven't told you the definition of this. It's a theorem that constructs it. And the definition is kind of complicated. But I contend that if you know these values and these functorialities and these computational uh, statements, then you can make computations in a lot of cases without having to know the definition of of this. Okay, so that's a outline of the main theorem. Before moving on, I'm happy to pause for any questions. Okay, so here's some examples of this. Um, it may be the case that some among you are familiar with factorization homology of EN algebras or E3 algebras. And there's a way of producing a, so if you have an E3 algebra A, the one-fold D loop of it will be a category that retains a E2 monodal structure. So this is an example of a braided monodal or E2 category. So one can ask, is this construction I mentioned, does it agree with the previously defined version of factorization homology? And I'm tagging it by the alpha version versus the beta version. Um, and the answer is yes. So if you knew what factorization homology of EN algebras is, um, this construction I just mentioned generalizes that. In a sense, it's allowing the E3 algebra to have more than one object. Um, and if you don't know what this is, then this identity is not helping understand what the left-hand side is any better. So let's specialize even further. One example of an E3 algebra is just an abelian group. And if A is an abelian group, then this becomes very familiar. It's labeled configuration space. So this is configuration of points in M labeled by the abelian group A. And this is it's in classical algebraic topology, it's called SP infinity for symmetric product, the infinite power of symmetric product. And it's studied in Dold-Tom theory. And there it's shown that the homotopy groups of it recover the ordinary homology. So, so in a sense, this construction, uh, it's it's producing it is generalizing the construction of Dold and Tom that produces a way of computing homology. So this is through Dold-Tom theory. And the takeaway here is that this new thing generalizes homology of M. Um, Another source of examples of graded monodal categories are perfect modules for an E2 algebra. And I'm not going to spend much time on that, but if this picture carries any meaning to you, if so, paint the ambient R2 with A and a dot in the center by a module V. And this is kind of in a picture indicating how A acts on V. And that as you vary V, they form a category. And if you insist that V be essentially a retract of a free, finitely generated free A module, that's what it means to be perfect. Anyway, so this is another way of supplying examples of braided monodal categories. But here's a key example that I mentioned earlier. If you take the Lie algebra, little SL2, um, there's a uh, there's a deformation through Hopf algebras of um, its universal enveloping algebra. The deformation uh, um, uh, that was first studied by Drinfeld in uh, very quite celebrated work in 1986. And it has it has the structure of what's called a quasi-triangular. Uh, the the coalgebra structure is quasi-triangular, um, and representations for that Lie algebra are was simply called quantum rep Q of SL2. If one looks at the finite dimensional ones, then that quasi-triangular structure on this Hopf algebra determines a braiding on this. So this is an example of the quasi-triangular structure determines a braiding on this category of representations. So this is the kind of thing that can be input into this construction. So if you take R to be that, then H0 of it is the skein module of M. And here Q is generic. Rigidity fails if you specialize Q to be a root of unity. So our work does not apply there. And my collaborator John Francis and I were aiming toward this for some time, and we were looking at the definition of a skein module in terms of skein relations and the like. And uh, there's a paper by Gunningham, Jordan, Safronov that pointed us to some previous work of Turayev that that solved for us how we could see the skein relations appearing from this. So this identity was greatly aided by some reinterpretations of skein modules due to Turayev. So in particular, that means the value in R3 is the skein module of R3, which is known to be rational functions in Q. And uh, so as I think many of you are familiar with, um, if you have an expression like excision that I mentioned down here. So this is a statement of excision. If you split a manifold, you have this relationship between that chain complex and the derived tensor product of these. Such a result um, is not, strictly speaking, compatible with applying H0, but you do get a long exact sequence on homology. And that long exact sequence on just at the bottom of it was observed in Cook's work. And so this identity, together with the excision result, is extending Cook's work to establish an excision result for skein modules. Um, Here's another example. This is a way of producing knot invariance using this setup. So given a knot in R3, and let's say it's framed, and framed here means um, the Gauss, to me, a frame knot is a knot equipped with a trivialization of its Gauss map. So that's a orientation of the knot, a normal framing, and then together with a compatibility of the resulting trivialization of the tangent bundle of R3 along the knot with the standard uh, framing of R3. So given a frame knot, um, you can do there's these two simple maps. So there's the map I mentioned before, that's just projection, and that's a proper fiber bundle. And then the frame knot determines a framed open embedding from S1 thickened a little bit to an R2, embeds into R3. And I mentioned the functoriality of this construction as oppositely functorial with respect to this class of morphisms and covariantly functorial with respect to that class. So one gets a composite map from the value in R2 to the value in R3. And those are the only two values that I gave explicitly. This value was the chains on the objects of R, and this value was the endomorphism of the unit. So in this way, given each object, we get an endomorphism of the unit. And let's just denote that object with those letters. So it's J, because this will turn out to be generalizing the Jones polynomial construction. V, because it depends on V of K. And indeed, if you apply this to where R is rep Q of little SL2, and for V to be the fundamental representation, the two-dimensional representation, of little SL2, um, then this will be a rational function in Q, and that is the Jones polynomial. So uh, so this is a way of producing knot invariance in a way that generalizes the Jones polynomial construction.
Can
Uh,
I ask one question?
yeah, please.
Uh, so knots and links are very much related with number theoretic objects, with primes and so on. Is there any number theoretic example similar to this one?
Say that again. They're related to what?
Uh, Knots
So,
and links are related to prime numbers
oh,
in
no,
num
number theoretic. Yeah.
yeah. So are there any number theoretic example or some version of this via arithmetic topology dictionary kind of thing?
Yeah. Uh, I have no idea. I love I'm aware of this dictionary that's every few months being amp you know enhanced.
Yeah,
But I don't know.
I see.
Uh,
Oh, thank you.
yeah.
Yeah,
Yeah. Yeah, that would be pretty interesting to know about. Um, and of course, what took place up here, the way I indicated this was given a point in this space. So this association was happening on the level of zeroth homology. And of course, one gets something much richer. Um, every framed embedding of a link in M, that entire space, the chains on it, maps to this chain complex. Um, so that's much richer than just what was achieved on the level of pi zero to recover the Jones polynomials. Okay, so far I've talked about, I gave a heuristic of a main construction with some nice features of it. I've talked about some examples and applications. Um, Let me now talk about some structural corollaries of that work. And one of them is the one-dimensional tangle hypothesis. So I'm talking about tangles of one-dimensional submanifolds in arbitrary ambient Euclidean space. The most interesting case being three-dimensional ambient Euclidean space. And uh, the main result that I mentioned um, implies the one-dimensional tangle hypothesis, which in turn implies the one-dimensional cobordism hypothesis. And here's one statement of that. So that by this, I mean one dimension. So this is the tangle category in which morphisms are one-dimensional tangles in Rn minus one cross D1. So morphisms are one-dimensional tangles in Rn minus one cross D1. So when n is equal to 3, this looks like one-dimensional tangles inside of inside of there as what a morphism looks like. Um, so this is the tangle category of one tangles in n-dimensional ambient space. And if you take X to be any other rigid n minus one monoidal infinity one category, then this is the space of all n minus one monoidal functors from the tangles to X. Evaluating on the object, which is just the dot in Rn minus one, reports an object in X, and the statement of the tangle hypothesis is that functor is an equivalence, or that map between from the Hom space to the moduli space of objects is an equivalence. And of course, the inverse is the most interesting. So in other words, given any object in here, one produces knot invariance, tangle invariance. So that's a logical corollary of the main result. It turns out that to prove the main result requires proving this result first. And so the reason I decided to focus on this content is I recently posted uh, a paper that just proves the one-dimensional Tangle hypothesis. Um, uh,
Excuse me. Sorry.
Another structural consequence is that so given any again any rigid n minus one monodal infinity one category X, so think rigid braided monodal one category, there's an action of the group of base loops of the orthogonal group on X. And if you forget the monodal structure, that descends as an action of the base loops on a sphere. And if you just look at the action on objects, that further descends as an action of um, base loops on projective space. So this is also on the archive. So just this consequence is also appears on the archive. Um, and in dimension three, we can these are pretty explicit. So if n is three, then this is RP2. And base loops of RP2 is, well, it's a homotopy type with infinitely many homotopy groups that are non-vanishing. And pi 0 is Z mod 2, so O of 1. In that case, there's an action of O of 1 on the space of objects, and that's just given by taking duals. Uh, pi 1 of this is Z, and what that determines is uh, an automorphism of every object kind of functorially among isomorphisms in those objects. And that turns out to be generalizing conjugation by a ribbon element. And I don't know in familiar terms what the action of pi 2 corresponds to, um, but it constructs such an action, um, and so on. So pi 2 of this space is Z mod 2Z. Um, wait, that's wrong. Uh, pi 2 is pi 3. Sorry, this is an action of Z. Um, and essentially, as a corollary, um, is this statement that as far as I'm aware, this has been a folklore statement that ribbon categories are SO3 fixed points of. So a ribbon category is a rigid braided monodal category that's SO3 fixed, and there was no rigorous construction of that SO3 action previously, and so once we constructed it, uh, then we verify this folklore statement. Um, I'll mention a couple um, guesses. So, um, well, uh, I conjecture that this action is true not just for one categories, but for infinity one categories. Uh, the methods that above don't quite do that. Um, so that's a guess. And also that if you have a rigid two-monodal category, whoops, infinity one category that happens to be SO3 fixed, then we conjecture that this chain complex only depends on the orientation of M, not the framing. Okay, so far I've talked about the heuristic of the main result. some applications of it, and these two logical corollaries of it that are themselves of independent interests. So what I thought I'd do now is state the main result with some more detail, and then I have material prepared to talk about the key ideas that go into the construction. Um, and as I said at the beginning, I invite comments and questions, and I'm happy to go in any direction that seems desired.
Before continuing, can I ask one question? Cobordism hypothesis is by Lurie, which states that n-dimensional TQFT is completely determined by n minus one dimensional TQFT kind of thing. Is this correct?
Yeah,
Or yeah.
yeah, that's a way of stating it. That's right. And in a sense, so this tangle hypothesis uh, says something similar. It says that a uh, like an embedded field theory, is is determined in ambient dimension n is determined by it in ambient dimension n minus one. And if you go down by induction to ambient, the lowest possible ambient dimension, that's just the essentially the objects. Like
So
yeah,
it
go
is
ahead.
like class field theory. I mean, everything depends on the base field kind of thing. In algebraic number theory, one major theorem is class field theory, which says that
Yeah,
arithmetic of the absolute Galois group is determined by the base field. I mean, it's quite similar in philosophy, at least.
I can see that. Yeah, yeah.
Is this theory related to Langland's correspondence?
Yeah, these are great questions that I don't know. I uh, as I talk with folks, I get questions along those lines, and I don't know that field well enough to give a good answer. My colleague here at MSU, Sam Gunningham, and uh, his um, his postdoc advisor, um, David Bensby, would really be great people to ask that type of question. Yeah,
I've got a bit of a naive question. You'll probably
yeah,
be able to answer.
yeah.
I was wondering what the connection is between n-connected objects and the coend that you pointed out earlier on.
And connected object and the coend.
Yeah.
So is the coend you're referring to like
Yes.
this coend? And the end connect, yeah, uh, it's an insightful question. Um, yeah, great. Uh, so let's see. So here's here. So if you take R to be, so it's going to be the D loop of chains of omega 3x. So
Okay.
omega is the space of base loops. Um, this is an E3 algebra,
Right.
and so it's the one-time D loop you can think of as a category, and it retains an E2 monodal structure. So this is an example of such an R. Um, then it turns out that this value is chains on the space of compactly supported maps from M to X. And um, so this is non-abelian Poincare duality. This is an application of that. Um,
Okay. Yeah.
and and now if you just saw this statement, so um, the right-hand side just references X. The left-hand side references the threefold base loops of X. Um, And uh, taking threefold base loops of a space, you lose information. You lose pi zero, you lose pi one, and you lose pi two.
Yeah.
Um, so uh, this might be a little perplexing then to see such an identity. And now,
Mm.
if you think about, okay, allegedly, I said that the left-hand side satisfies this Cohen formula. So you could
Mm.
wonder, is it possible to see that the right-hand side does independently? And if so, then you can break up a manifold in this way, ultimately to Euclidean spaces, and then you to verify this, you just need to verify when M is R3,
Ah,
where it's
yeah,
tautological, right? So
I
this
see.
to prove this is essentially logically equivalent to showing that this also satisfies this. So to answer your
Yeah,
question now, um, the right-hand side satisfies excision only if X is 3 connective,
I see. Yeah, yeah.
which,
And so all the
yeah,
yeah, go ahead. Yeah.
yeah, which is what you might have guessed because of the lossiness of that
Mm.
R only feels the 3 connective cover anyway. Um, and in fact, right, in fact, uh, let's see, this statement is, oh, wait, I said only if. Um, I, I, so if that is 3 connective, then that's true. And for different reasons, if you
Ah,
all, so if you take R, so alternatively and better, if you take R to be um, essentially chains on the twofold base loops, but now you regard this as a two-monoidal one category, in fact, a one groupoid. So you're thinking of the so the space of twofold loops as an infinity groupoid, and as so it's two-monoidal. Um,
right.
so this now remembers a little bit more. It remembers pi 2 of the space.
Interesting.
Then same comment, and then if X is 2 connective. So that's very insightful to notice the relationship between this excision and connectivity. And
Mm.
yeah, there is a very tight relationship.
Okay, great. Thanks.
Yeah.
I
Excellent.
think I think you described Fubini theorem and how is the uh, cup product and Cartesian product Mayer-Vietoris in this theory
How is the Cartesian product and Meyer-Vitouris in the story?
and cup product.
And cut product? Yeah. So cut product is distinctly not in the story.
Yes.
This is like generalizing homology, though maybe you could maybe by your comment about Cartesian products, you could say what is the coalgebra structure on homology, right? Because that's what's dual to cut product. Um, and I stated this in yeah. So for just as a remark, uh, you know, in good old topology, going from top to chain complexes by taking chains with values in your ground ring. Um, uh, this carries it lands not in chain. So there's a lift to coalgebras, commutative coalgebras. I'll say commutative, so co-commutative algebras in chains. This is an observation. And uh, that's one way of, so we can then take linear duals and see that taking cochains is not just valued in chain complexes, but is valued in commutative algebras, codifying the cut product, right? So this is a homology way of stating that. And so there's this observation of this natural lift has to do, of course, with uh, like the Punnett
And also,
formula.
how is it dual theory? Yani, we
Oh, is
have,
that
I
what?
think, dual theory, dual.
Um, so if we take linear dual, um, this goes to chain complexes op, right? And this goes to commutative algebras in chain complexes.
I think there is a cap product you defined.
Uh, I think it's the like the coalgebra structure on chains.
Hmm.
Um, so, well, I bring this up in response to that comment because I stated this all over K, but there's a more general statement that is true. Uh, we don't need to be working in this category, but we can work in any symmetric monodic category. And if we do
Hmm.
it top and then apply chains, then that recovers the coalgebra structure on it, which the way I see it is dual to the cut product. So the version of this main theorem, not saying over K, i.e. in chain complexes, but where this output is a space, I think could recover the structure that you were alluding to.
Okay,
But
thank you.
I haven't thought too much about it. That's an interesting question. Um, okay, let's see. So I gave a go at stating it with more detail, the main theorem. Um, I think what I'd like to do is uh, focus on is indicate that there's a class of geometric things of manifolds that arise in this study, and I want to focus on that. So I see a lot of clutter here. I'm going to focus on this term, uh, but to contextualize it. So um, given an object here, which is a n minus one monoidal infinity one category, and I'm allowing enrichment anywhere, as I was just alluding to, be that in chain complexes or spaces or any place. This is true in a lot of generality. So given a n minus one monoidal infinity one category that is rigid, um, one can construct um, functors from this peculiar category of manifolds. And the values are as I described. So somehow this category, its morphisms are were referenced earlier when I was talking about the functoriality of this. So some morphisms are frame diffeomorphisms. Some other morphisms are open embeddings, and others are the opposite of these proper fiber bundles. So this is a very peculiar category that was designed just for this kind of setup, this theory. And I'd like to focus on what an object in this category of manifolds is. So an object is, it's convenient to call it a bracket n minus one comma n manifold. I hope that evokes the dimension of these things ranges between n minus one and n. And what I mean by that is the following two pieces of data. A manifold, possibly with boundary, and a proper embedding of an n minus one manifold into it such that the boundary of M is contained in that proper embedding. So, for example, if n is equal to 3, then a surface, that's an example. Also, a 3-manifold with boundary. So this is not compact. It's a This is R2 across the one disk. So it's all the goo inside. That's an example. But another example is R2 with D1 inside, together with this additional that's M sub 2 inside of M in this case. That's the properly embedded 2 submanifold of M. So it includes the boundary, but it also includes something else. And together with a type of framing data that maybe I won't go into right now. So examples of such a thing are parallelized 3-manifolds. Other examples are surfaces with some framing data. And here's the class of examples that I'm wanting to focus on. So if you pick a 3-manifold, and W here is a graph, and U is a regular neighborhood of it. So here you can see the graph, and I'm indicating a regular neighborhood of it. So that open neighborhood, U, is certainly a 3-manifold. But the fact that it's a regular neighborhood of a graph gives it more structure. You can look at these little hyperplanes perpendicular to each edge of the graph, and that determines, that determines this ensemble of surfaces properly embedded inside of it. So in a sense, this is like, I think of it as the Poincare dual of a graph, the 3-dimensional Poincare dual of a graph. It's this way of thickening it. And you retain the data of the graph. You can recover the combinatorics of the graph just from this picture. The top dimensional cells correspond to the vertices. You put an edge between two vertices if they have a common boundary interface. So this thickened thing is it's equivalent data to the graph. And essentially, this is why this category of manifolds is invented. It's so as to accommodate these kind of pictures. And now this category, I neglected to say that early on, but this category is kind of it's very surprising. Say fantastic in the original sense of the word of like fantasy. So let's just shorten the notation M for that category I just alluded to earlier. And there's a full subcategory D, which consists of those such that it's comprised of just these pictures and a ball with finitely many patches on the ball. So I drew the corresponding graph in orange here. So in other words, an object in this subcategory is an n-dimensionally thickened graph. So that's not every object in here is of that form, because some objects in here are like closed n-manifolds with no boundary or anything. And there's this subcategory consisting of the thickenings of graphs. And there's this category is so peculiar that it has this property that if you have an object in a thickened graph, and let's just say a framed manifold, a frame 3-manifold, HOMs in this category from that thickened graph to the manifold correspond to the following. So if it's just of this form, then HOMs correspond to compact sub-1 manifolds. So
That's
tangles.
so that is this the strata?
What was that?
Would you say that these are the strata of that manifold?
No, it's like if this is if you take this to be like R3, so it has no strata, and this to be R2, then HOM from
Okay,
R3, R2, um, the collection of such is precisely the same as the compact the links inside of R3 that are framed. So
right.
and we saw an example of how a link determines such a map. Is you do the opposite of the projection off the circle and followed by the embedding. In fact, every morphism from R2 to R3 corresponds to that. It's a very weird category. And if if D is a ball with uh, finitely many patches, then there's a similar statement in terms of not sub one manifolds, but graph tangles. So here we saw that so this in R3 is an example of a morphism from R2 to R3. And uh, in this case, we see that like um, yeah. So there's a graph tangle, and all the valence is equal to 3 in this graph tangle. And this will correspond to the ball B3 with 3 patches. So this will correspond to a little tiny regular neighborhood, a three-dimensional thickening of that graph. So it's somehow like this is governing, like it's coloring this. Like if we give this color 1, 2, 3, 1, 2, 3. It's a very weird category. Um, and I am have a lot of optimism that a lot more can be done with this category than simply these results indicate. So I'm cognizant of time, and it, yeah, I certainly had plenty to. So I'll share these notes, and um, maybe in the last minute, I'll just share. Um, I'll just draw your attention to this key lemma that's in that can be found in Appendix A of Higher Algebra by Lurie. Um, this I call it the hypercover lemma. I have found it to be by far the most useful tool for connecting anything of a geometric flavor to anything of an infinity categorical nature in a way that's genuine. Using this hypercover lemma, um, it's the only hope that I'm aware of for essentially like computing colimits in infinity categories that arise from geometry. So I'm deciding to finish this talk by just drawing your attention to it because maybe you will find utility from this as well. And the statement is this. So if you have any topological space, it's amazing. There's no conditions of Hausdorffness or pair compactness or anything. And if you look at a functor, from a category K to the poset of opens, then well, you certainly get a map from the homotopy colimit of that diagram of those opens to X. And that map is a homotopy equivalence, provided this very checkable condition. And that checkable condition is that the full subcategory, so for every point in X, the full subcategory of all uh, the objects of K uh, whose value contains that point, so long as it has contractible geometric realization, then this is true. And just appreciate that these are open sets. So this is profoundly not generally um, a cofibrant diagram in a model category or anything like that. That's the other technique for showing this kind of stuff is to take cofibrant replacements, whatever. And this is very far from the kind of statement that is achieved from model categories. So yeah, and I'll just indicate the way that we tend to apply it in this work is by contemplating. So we take X to be the moduli space of all tangles. So this is, here we see, I'm just drawing a picture of R2 cross D1 with an extra slice in it. And you can look at the moduli space of all possible tangles in here. So all tangles. This is an infinite dimensional topological space as you move the tangles around. Um, and there's a subspace of it, of those tangles that are transverse to that intermediate slice. That defines an open subset. Uh, that defines an open in this of all that are transverse. The fact that it's open uses that we're working in the smooth context, etc. And if one can organize a category, so for each slice, you get an open. So each slice determines an open U inside of X. And well, this collection of opens satisfies this checkable condition, and therefore you know that the homotopy colimit of all the space of tangles that are transverse to a given slice, the homotopy colimit of those is the moduli space of tangles with no transverse condition. Um, so I hope that this evokes like how to use. I mean, it's a nice application of this lemma that's kind of non-obvious, and that's the guts of the proof of much of this theory.
Right.
Well, I really appreciate your attention and opportunity to give a talk here. So thank you.
Thanks, David.
Uh, Thank you very much, David, for this wonderful talk and for your patience of answering our questions. So, any more questions or comments?
Yes. I want to ask about the tangroids. So can we apply this calculation to tangroids with end category of tangroids,
A
or
tangoid?
maybe half monoidal category?
You might need to teach me something. What did you say, tangoids?
Yes, a tangle with ends.
And with ends, is that like, is this an example?
Yeah.
Is it?
Yes.
I guess that to me that I would call that a tangle, or how I was using the term tangle. Th this was a tangle.
Yeah, so these
Um,
these two coincide, right?
yeah, so I guess like the hierarchy of, there's knots, those are connected closed submanifolds, and then there's links, um, and then there's tangles, and these are like connected without boundary. These are not necessarily connected, but they have no boundary, and these possibly have boundary. So, or that's the way the terms that I've been using in this talk abide by this. So maybe what you were saying is tangloid is what I was calling tangle all along.
So can you share your this notes?
Yes,
It
of
is
course.
okay. Thank
Excellent.
you. Yeah.
I just have one more question.
Yeah, please.
I was reading quite a bit about sifted co-limits and the sifted co-completion of a category. And I was kind of wondering if there was maybe a bounded derived category of complexes floating around here.
Um, yeah, great. So there's a yes. Um, okay, so I didn't spend much time on it, but I mentioned the main theorem here. And so let me point to it. So um, this theorem is valid for categories enriched in symmetric monadal categories, and I said, or I didn't say, but I wrote that are tensor presentable. So it turns out actually being so actually this symmetric monadal category for this theory to work, this symmetric monadal category doesn't need to be full on what's called tensor presentable, but rather satisfy. So V admits sifted colimits.
Okay,
It doesn't have to admit all colimits, and this distributes over sifted colimits.
excellent. Okay,
Yeah. So the bound. So yeah. So bounded derived categories are examples of such uh, a enrichment site.
okay.
But there's I wouldn't say there's any like contribution that this
Uh,
work lends toward the study of bounded derived category or of such.
okay. And what if we were talking about directions in that sense?
Mhm.
Where would the direction of this work be headed if bounded derived categories are not of interest?
Um, my instinct is probably it would not this work would not inform that work. Um,
Okay.
uh, yeah.
But it's heading maybe towards spectra.
It accommodates spectra as right now. Yeah.
Okay.
Um, yeah, let's see. So um I I think I don't think this is ingenuous to say. I think it's related to these prompts. Is So a lot of this work uh, involves a careful analysis of stratified spaces and how they move in moduli. Um, and in thinking a lot about stratified spaces, uh, this got us thinking about um, so for X, a stratified space, we can look at sheaves on X, the category of sheaves. We could also, yeah, so we can look at the category of sheaves on X and what how does the stratification persist on this category? Is this stratified in some sense? So this is a category. Um, and the answer is yes. And this is developed in a paper called, um, and actually before saying that, also for X, um, for X, a stratified scheme over
Yeah.
over any field, say, then we could look at QCO of X and ask, that's
Right.
a category, and is it stratified?
I see. Yeah.
And I say, is it stratified? But more like, what structure on this category reflects that the scheme was stratified in the first place? So the answer to both of these is yes. And there's a book titled Stratified Non-Commutative Geometry.
Okay.
Uh, of myself, um, Maisel G. and Rosenblum. As I mentioned at the beginning, these are the other collaborators I was alluding to, and uh, and in there we study uh, uh, just purely categories like the bounded derived category and stuff. There's no tangles or anything like that. And the main result is a reconstruction theorem. Rebuild to build um, sheaves on X or quasi-coherent sheaves on X from sheaves on the strata. It's a reconstruction result. And actually, there's two reconstruction results. And if you match them together, you get these very strange dualities resulting in what's called reflection. Um,
Interesting.
it has to do with mutants in quiver representations and stuff like that. So anyway, it's not directly related to this work, but the the development of stratifications that we did for this work blended to this other stuff that may be more relevant to study of
So,
bounded drive categories and stuff.
Any more questions or comments?
One last question. There
Okay.
Yeah.
is there is any relation with K-theory or algebraic K-theory of the story?
Yeah. These are um, uh, in a sense, yes. Or so yes. Up above that, I was doing a three-dimensional discussion, but if we specialize to n equals one,
Yeah.
then then if you just have for R just a category, um, and it could possibly be linear, and I allow it so more general than category as an infinity one category, but category works just as well, then this symbol over the circle of R is recovers the Hochschild homology of the category. And this is THH over V. So this is if V is chain complexes over something, and this is in the case that V is equal to spectra.
wow.
Um, and and so now endomorphisms in this weird category that I mentioned, this is that fantastic thing. In dimension one, endomorphisms of the circle for it is this is a simple computation that is the natural numbers with multiplication, and it acts on the circle group. So that's the circle group. So the monoid of endomorphisms in this fantastic category has this description, and this corresponds to isogeny, and this corresponds to rotation. So i.e. covers. And because I mentioned that this construction of this is so rich that it's actually, it's a functor on this category. So you automatically get an action like this. And that action recovers what's called the cyclotomic structure on Hochschild homology, or THH. And that's relevant because if you take the K-theory of R, there's this Dennis trace map to the Hochschild. I'll use the T because that's where it's most interesting, to THH. And it is known to be invariant um, with respect to the cyclotomic structure. In fact, it comes from, so this is essentially this on a point. And as I set up there, this is that value on a circle. And point to circle, that's a proper fiber bundle. So you get a map going this way, and that recovers the trace map in algebraic K theory. And the fact that this map is obviously invariant with respect to the endomorphisms verifies that it actually lifts to here. And this is what's called the cyclotomic trace, or sorry, topological cyclic homology. And that's the cyclotomic trace. Um, and that's an incredibly tight map. This turns out to be um, this is it's sort of like an atoll map. Um, in the sense that if you modify R by a square zero extension, um, then this operates as a pullback. So if you have a nilpotent extension, um, then this is not my work, but this is Dundas, Goodwillie, McCarthy.
The homotopy coherent diagram.
That it's actually a pullback
Right.
of spectra. And this is the Dundas, Goodwillie, McCarthy theorem. Um, these are the downward arrows of the cyclotomic trace maps. And this enables computation of a huge class of tons of K theory. So yeah, anyway, so that cyclotomic trace map, it can be constructed using these methods in dimension one. So
Wonderful.
it is very much related to, in a sense, to K theory. And this work, if you want to see, uh, um, if you want to see this, there's a series of papers, myself and Basil G. and Rosenblum, that are a mix of published and on the archive.
Thank you.
Yeah.
Many thanks.
Okay, so let's thank David once more. And thank you very, very much. We will meet 2 weeks later in another higher structure seminar. So have a good day, David. You are starting your day now. And
Yeah, yeah, yeah.
and
Nice to meet you, Ilhan.
oh yeah,
Um,
nice meeting you.
I-
So
I'll
Nice
send
to
you
meet
the
yeah,
notes. Yeah,
bye bye. See
nice
you.
to
you
Bye.
connect.
later.
Bye.
Yeah,
Yeah.
thank you very much.
Bye bye. Thank you.